Let's take a moment to think about your coffee mug, your phone, or even a space shuttle. Believe it or not, all of these rely on ceramic materials. But what exactly are ceramics? And why are they so strong, yet so fragile at the same time? The secret lies in their atomic bonding. From a chemical point of view, we define ceramic materials as inorganic, non-metallic solids that consist of metallic and non-metallic, or two non-metallic, elements. In other words, ceramics are what we're left with when we take away metals and organic materials, including wood, polymers, and anything that was once alive. Generally, ceramics combine high hardness, thermal resistance, a good electrical insulator, and exhibit high chemical stability, properties that make them indispensable in both daily life and advanced technology. Yet, despite all this, they often suffer from brittleness. So, what causes this paradox? It all starts at the atomic level. Ceramics are held together by either ionic bonds, covalent bonds, or a mix of both. Ionic bonds involves binding a metal element with a non-metal, while covalent bonds results from binding two non-metals. These bonds determine how the atoms are arranged and how the material behaves. In ionic bonding, a metal atom gives up electrons, which are accepted by a non-metal. This transfer allows both elements to achieve a stable, full valence shell, like noble gases. The result: positively and negatively charged ions that are held together by strong electrostatic, or Coulomb, forces. This creates a highly stable structure, which explains the high melting points and hardness we see in many ceramic materials. However, these same ions are locked tightly into a crystal lattice. They can't move freely. That's why ionic ceramics don't conduct electricity. And there's a trade-off. Because the ions are fixed in position, ionic ceramics tend to be brittle. Even though they're hard and rigid, when enough force is applied, like a hammer strike, the layers of ions shift. Suddenly, like charges are forced next to each other, and they repel. That repulsion causes the structure to fracture rather than bend, and the ceramic shatters. Now let's talk about covalent bonding. In this type of bond, non-metal atoms share electrons to achieve a stable, closed-shell electronic configuration. The result is strong, directional bonds that tightly hold the atoms in place. This kind of bonding gives ceramics their outstanding strength, thermal stability, and resistance to chemical attack. However, just like with ionic ceramics, these materials are brittle and prone to fracture under sudden force. So how do we know whether a ceramic will have ionic or covalent bonds? It comes down to electronegativity, a measure of how strong the atoms attract electrons. A large difference in electronegativity, like between a metal and a non-metal, leads to ionic bonding. A small difference, typically between two non-metals, results in covalent bonding. This subtle difference has a major impact on the material's behavior. Understanding bonding isn't just chemistry trivia, it's essential to engineering. Need a ceramic that can withstand extreme heat, like a jet engine or spacecraft? Go for ionic or covalent ceramics. Need a stiff and electrical insulation material? Again, bonding gives us the answer. This understanding helps us classify ceramics into two main groups, traditional and advanced. Traditional ceramics include materials like clay bricks, tiles, and porcelain, common, functional, and widely used for centuries. But when performance demands go beyond the everyday, we must turn to advanced ceramics. Did you know that ceramics are used in bulletproof armor? Ceramic armor plates are significantly lighter and tougher than steel plates, which is why they're often used in military and also in spacecraft, automobile engines, and electronics due to their ability to withstand intense heat and pressure. Ever had a dental crown or a bone implant? Then you've already benefited from ceramic technology. Zirconia-based ceramics are revolutionizing dentistry, offering the strength of metal with a natural look and feel that blends with the human body. Now let's talk about jet engines, where hotter means more efficient. But to survive that heat, engines rely on thermal barrier coatings, and the secret behind those coatings: a special ceramic called yttria stabilized zirconia, YSZ, built to handle extreme thermal cycling without cracking under pressure. And if you're looking for wear resistance, meet cubic boron nitride, the second hardest material on Earth after diamond. With its diamond-like structure, it's a go-to for abrasives, grinding wheels, cutting tools, armor, and precision engine parts. From the battlefield to your body, from the dentist's chair to deep space, advanced ceramics are shaping the future of materials science, one atom at a time.